Let me quickly remind you what you need for a function phi from one group G to another group G bar to be an isomorphism. This is an isomorphism if three things happen. Phi is 1-to-1, phi is onto, and 3, phi is operation preserving. You can abbreviate that OP, but you should, if I put this definition on the test, say what that means. It means phi of AB equals phi of A times phi of B for all elements AB in the domain G. That's what operation preserving means. If I also asked you what 1-to-1 and onto means, which I could, you should be able to state that. Let's go ahead and remind you as part of reviewing for the exam here. 1-to-1 in this context would mean if the outputs are the same, the inputs must have been the same. That's sort of the way I think of it. If the outputs are the same, phi of A equals phi of B, that implies that A equals B. Oh, that's supposed to be a B there. That implies that A equals B. If the outputs are the same, the inputs must be the same. Alternatively, another way to think of this is if the inputs are different, then the outputs must be different. That's really the contrapositive of that implication. That's what 1-to-1 means in any context for a function from a domain to a codomain. Given A and B in the domain where this is true, it follows that the A and B must be the same. Onto means given something in the codomain, I'll call it little g bar, in capital G bar, there exists an element of the domain that gets mapped to it. Exists a little g in capital G such that phi of little g equals G bar. Give me something in the codomain over on the right. Is there something in the domain on the left, if you make a blob picture, that gets mapped to it? If there is, no matter what element of the codomain I pick, then the function is going to be onto. So you should be able to state what those things mean as well. Let's look at some examples, though. First example in the book, we take the additive group of real numbers and map it to the positive real numbers, which I'll write like this. This is assumed to be under addition here. It is a group under addition. This is assumed to be under multiplication. It is a group under multiplication. They're both closed. This one's closed under addition. This one's closed under multiplication. The associative property works. 0 is the additive identity. 1 is the multiplicative identity. Additive inverses of, for example, pi would be negative pi. You take the opposite of the given numbers. Multiplicative inverses, for example, of pi would be 1/pi. And we can just focus on the positive real numbers here. That is still a group. We can ignore the negative real numbers. If we define this by, well, essentially any exponential growth function, that's an example that works. The textbook picks 2 to the x. We know from pre-calculus and calculus that this function is 1-to-1 and onto. If the domain is all real numbers, and the codomain is all positive real numbers, I put an open circle there at the origin. Not only does it pass the horizontal line test, making it 1-to-1, no horizontal line goes through it more than once, but it's also onto if the codomain is considered to be R+. Actually proving those things is something we took for granted in pre-calculus and calculus. It's harder than you might imagine because you really have to define what 2 to the x truly means as a real valued function, as x varies over the real numbers. And that's more subtle than you might imagine. Like, what does it mean to raise 2 to the pi power? It's really a limiting process. Is it operation preserving? Is phi OP? You got to be really careful here. You got to realize what the group operations are. For the domain, the group operation is addition. So I do not write A times B here or X times Y. I write, say, X plus Y. The group operation is addition. The formula would say that's 2 to the X plus Y. I'm wondering, does that equal, think about the codomain here, the operation is multiplication in the codomain. Does it equal the product of phi of X and phi of Y? I'm using multiplication because that's the operation of the group. That's the codomain here. Does it equal 2 to the X times 2 to the Y? Yeah, these are true. You've known that for a long time. These are equal. Equal. It's a property of exponents. So it is operation preserving. This is an isomorphism. And we would write this kind of notation that R is isomorphic to R plus. Once again, you need to realize that when I write this, it's understood that this R is a group under addition, and R plus, the positive reals, is a group under multiplication. If we're going to be a little bit more careful about it, we might emphasize that by writing this kind of thing. We might write an R with a plus sign in as an ordered pair and say that's isomorphic to R plus as an ordered pair with a dot for multiplication. Next example. I'm not going to prove everything here, but I just want to tell you about it and maybe hopefully you believe it. Any infinite cyclic group is isomorphic to the integers. Any infinite cyclic group is isomorphic to the integers, and any finite, can I spell finite? Finite cyclic group of order n is isomorphic to Zn. This is a claim. Essentially, you could call this a theorem. I'm not going to fully prove it, but I want to write down some things that would help you believe it. For example, if G is cyclic and the order of G is infinite, to prove that it's isomorphic to Z, you'd have to come up with an isomorphism. Guess I didn't officially define isomorphic. I defined isomorphism. When there is an isomorphism from one group to another, then we say those groups are isomorphic. If such a phi exists from G to G bar, then we say G and G bar are isomorphic, and that's when we write what I've been writing here. This is not really an approximately equal to, it's a symbol for isomorphic to. That's what I used here. If G is cyclic and it's infinite order, to prove it's isomorphic to the integers, we'd have to come up with an isomorphism. How? How in the world? You don't even know what G is. It's an arbitrary infinite cyclic group. Well, we do know it has a generator. This would imply there exists an A in G such that G is generated by A, consisting of all powers of A as n ranges over the integers. And the order of A must be infinite if G is infinite. So a to the n being the identity, the only way that can happen is if n is 0. There's no smallest positive power bringing you back to the identity. There would also be no biggest negative power bringing you back to the identity, because the order of G is infinite, therefore the order of A is infinite. Somehow that must be useful in coming up with the isomorphism. How? Maybe use the fact that Z's got a generator, right? 1. Also has a second generator, -1. What should I do to define the isomorphism? Maybe I should, A is kind of acting like 1 is. Maybe I should map A to 1. Maybe I want to define phi from G to Z by the formula phi of A equals 1. Maybe that's the way to do it. But wait a minute, that's only saying what A maps to. What about everything else? What about A squared and A cubed, etc.? Well, wouldn't it make sense to map A squared to 2 and A cubed to 3 and A to the 4th to 4, maybe? A to the 0 power to 0 to 0, A to the -1 power to -1, etc. Yeah, that's what you do. And essentially by extension, phi of A to the n equals n for all integers n. That is telling you what everything in G should get mapped to, because everything in G is a power of A. Is it operation? Is it 1-to-1 onto an operation preserving? Let's think about 1-to-1. I guess I am almost doing the proof here. What does 1-to-1 mean? It means if the outputs are the same, the inputs must have been the same. If phi of A to the m equals phi of A to the n, by this formula, that means m equals n. And if m equals n, then definitely A to the m equals A to the n. It's 1-to-1. Onto, given m in Z, what gets mapped to it? I hope it's pretty clear. It's A to the m. It's onto. It's very quick proof. I mean, I should really write some words to make it a true proof. Is it operation preserving? The operation in G is multiplication. What's phi of A to the m times A to the n? Multiply those by adding their exponents. And now looking at the formula for phi, that's the same as m plus n. And that's the same as phi of A to the m plus phi of A to the n. The operation in the G group is multiplication. The operation in Z is addition. This is enough to say it's operation preserving. Essentially, I did do the proof. Essentially, this is the proof. What would the proof be in the case where G is a finite cyclic group of order n? Could I maybe just modify this one? I think so. I won't actually write it down, but just look and think with me here. If G were a finite cyclic group of order n, so its order were n, I'd replace that infinity with an n. It would still have a generator. It would still exist in A in G so that this is true, but A would have order n. N would be the smallest positive integer, right, bringing you back to the identity. But maybe I should still map A to 1, but not as an element of Z, but as an element of Zn. And I do know Zn is generated by 1. 1 is one of the generators. So I am mapping a generator to a generator. Maybe that's a good thing. Would all this still work? If phi of a to the m equals phi to the of a to the n, by the formula, that would mean m equals n. Yeah, because it would still be the same formula, although, okay, there is an issue. I think there is an issue, actually, though, that I sort of skirted over here, if we're in this case of a finite cyclic group. And the question is, does this formula make sense? Really, it doesn't if it's for all n in Z. Because with a finite cyclic group, it cycles. If, for example, it has order 6, a to the 8th would be the same as a squared. And this formula would be, say, we're mapping a squared to 2 and a to the 8th to 8. That doesn't make any sense. So it's the formula that's going to be the key thing that you got to modify. You'd really have to say, if the order of G is, well, n, I'm going to map a to the m, say, to m mod n is the key. That would be the key difference. For example, if the order of G is 6, then phi of a to the m is going to get mapped to m mod 6. That's going to mean, for example, yes, a squared is going to get mapped to 2, but it also would mean a to the 8th gets mapped to 2, a to the 14th gets mapped to 2, a to the 20th gets mapped to 2, which is a good thing because since a has order 6, a squared, a to the 8th, a to the 14th, a to the 20th are all the same element if a has order 6. They better map to the same thing if this formula is going to make sense. But yes, you'd still have to prove it's one-to-one onto an operation preserving. I think it wouldn't be too terribly hard. I encourage you to think about it. And rethink about what I said here. It really is as easy as I was trying to make it. Maybe you're falling asleep and you weren't keeping track of it. Hard to pay attention here. But rethink about it after class. And you'll see that at least in the infinite case, these are pretty easy.